Okay, going back to what we have in working with inner products, and this time testing out matrices. And again, we still had the same four axioms. Now, looking at what we have in working with matrices, and we have just as an example, and we have for two given matrices A, which we have as a 2 by 2 array, and likewise with the matrix B with the respective 2 by 2 array. And okay, so if we let these matrices be in the vector space where we have m of 2 and 2, and we're to show that the function defines an inner product, okay, on the matrix space. And if we have the inner product A and B to be A sub 1 1 B sub 1 1 plus A sub 1 2 B sub 1 2 plus A sub 2 1 B sub 2 1 plus A sub 2 2 B sub 2 2. And okay, now we have A for what we have with A and B. Okay, so we have for the inner product case, so we have these items. And if I were to take the commutative equivalent, okay, that is going to be the same, but just the rearrangement. And so we had the subscripted values to be the same for what we have in the A and B expressions alongside one another. Okay, so we had the inner product of A and B will be the same as the inner product of B and A. Okay, so the first axiom is going to be satisfied, and we have with the second, okay, so if I have A and B plus W, and what's going to happen here is if I have the distribution of A sub 1 1 and you have over B sub 1 1 plus W sub 1 1, and do the same thing for the subscripted 1 2 2 1 and 2 2 combinations, and I look at combining what I have with the A and B pairings as well as the A and W pairings, these will translate to where we had the sum of the inner products of A and B and A and W. So the second axiom would be satisfied, and we have with the third axiom where we had the scalar. So if I distribute C over the inner product of A and B, so we have with the function, you have C all over these four items. And if you notice, okay, so clustering what I have in the C and A sub 1 1 all the way up to A sub 2 2 combinations. And this is going to translate out to where we have C times, again, the inner product of A and B. And so we have just taking furthermore. And so we have that this is going to be equal to, we have C times A and B. Okay, and so again, the third axiom is going to be satisfied. Now, for what we have in the case of testing out the fourth axiom, now you're going to have the inner product of B and itself. Okay, and we have, okay, just looking at taking the inner product, so you have with replacing the matrix A with B and looking at the elements. Okay, so we've got B sub 1 1, B sub 1 2, B sub 2 1, B sub 2 2 in lieu of what we have with our A subscripted terms. So we got the duplication of matrix B and looking at what we have in operation with the algorithm, but where we're going to have exclusively subscripted B terms. So replacing what we have from the formula for the inner product of A and B, where A is replaced with B and the subscripted lowercase a terms are replaced with B. And guess what? So with the pairings, okay, we'll have B sub 1 1 squared all the way out to B sub 2 2 squared is going to end up having the sum to be greater than or equal to 0. Again, the sum of squares will be only non-negative. So the destination of the sum of the squares will be either 0 or positive. And the sum is going to be equal to 0 if and only if we have all of B sub 1 1 to B sub 2 2 is equal to 0. And guess what? So there's nothing hanging in the balance in terms of any potential for any one of these four components to be non-zero. So for B is unequivocally 0 since we have all of B sub 1 1 to B sub 2 2 to be equal to 0 for this equation to be equal to 0. So it's going to turn out that we have for this function, for what we have for the inner space of a and b to be equal to a sub 1, 1, b sub 1, 1, all the way out to a sub 2, 2, b sub 2, 2, that is going to be a function that does define an inner product in that particular matrix space. And if we're looking at finding another inner product and also looking at the norms of a and b and also the distance between the matrices, we have, first of all, so we have for 29, we have the matrix A consisting of, in the top row, we have 2, negative 4. Bottom row, we have negative 3, 1. And for B, we have negative 2, 1 in the top row and 1, 0 in the bottom row. And for the inner product, okay, so we have, by definition, you have 2 A sub 1, 1, B sub 1, 1, plus A sub 1, 2, B sub 1, 2, plus A 2 sub 2, 1, B sub 2, 1. And we have plus 2 times A sub 2, 2, B sub 2, 2. And so you have just the corresponding parts here for 2 A sub 1, 1, and got 2 times B sub 1, 1, negative 2. A sub 1, 2, we have negative 4. And B sub 1, 2, we have 1. And then we have A sub 1, 2, we have at negative 3. And we have, in the case of B sub 2, 1, we have 1. And then for 2A sub 2, 2B sub 2, 2, we're going to have 2 times 1 times 0. Okay, and so for what we have throughout, okay, so we got negative 8 plus negative 4 plus negative 3 plus 0. So this will come out to negative 15. So the inner product is going to end up at minus 15. And for the norm of A, that's going to be equal to the square root of the inner product of A with itself. And so in what we have for the inner product of A and itself, so you got the matrix A duplicated and carrying out the formula for what we have throughout, but with the terms in B replaced with A and the same subscripted amounts. Okay, so you're going to have like 2 A sub 1, 1 times A sub 1, 1. Again, replacing what we have in B with A, but the same subscript, same positions. So you got 2 times 2 times 2. Next, we have negative 4 times negative 4, followed by negative 3 times negative 3, and then we have plus 2 times 1 times 1. And for the sum of the products, we have 8 plus 16 plus 9 plus 2. So this will come out to 35. And so for the norm of A, this will be the square root of 35. And for what we have for the norm of B, so we're looking at the square root of the inner product, okay, for B and itself, okay, and so applying the matrix B, where again we have negative 2 and 1 for the first row, 1 and 0 for the bottom row, and following through, so we're going to have the products to be 8 and 1 and 1, and whereupon we're going to have the sum to be at 10, and the square root of 10 is going to be what is going to be the norm of B. And for the distance between matrices A and B, okay, so we have for A minus B, okay, so looking at subtracting the corresponding elements from matrix B from those in the same position in matrix A, we have 4, negative 5 in the top row. Bottom row, we have negative 4 and 1. And looking at duplicating and looking for the inner product of A minus B and itself and following through with our formula. And so we're going to have in the A sub 1, 1, B sub 1, 1, A sub 1, 2, B sub 1, 2, 2, 1, 2, 1, 2, 2, 2, 2. We're going to have duplicate values since we're looking at A minus B with itself. And for what we have upon taking the products, so we're looking at 32 plus 25 plus 16 plus 2 will add up to 75. And we're going to have for the distance between A and B, again, that is going to be the square root of the attained inner product value of 75, and lowering in reduced radical terms, that distance will come out to 5 times the square root of 3.